You're looking at telescope data from December 2024, and something's wrong. There's an object moving through our solar system at 87,000 miles per hour, fast enough to escape the sun's gravity forever. It came from interstellar space. But that's not what's keeping astronomers awake at night. Behind this visitor, designated 3I/Atlas, stretches a plume of venting gas over 10,000 kilometers long. That's wider than Earth itself. Here's the problem: this comet is too far from the sun for solar heat to cause this eruption, too cold for water ice to sublimate, too stable for a collision to explain it. Yet you're watching it spray material into space with the force of a rocket engine, and it's been doing this for weeks. Every rule we've learned from studying comets over the past 400 years says this shouldn't be happening, but it is. And the most shocking part, the answer scientists finally discovered, reveals something profound about the alien worlds. This comet came from worlds that exist in star systems you'll never see, but whose secrets just arrived on our doorstep. If you're captivated by real cosmic mysteries that science is solving right now, discoveries that change how we understand the universe, you'll want to see where this goes. Like this video if you're ready for a deep dive into one of the strangest objects ever detected, and subscribe so you catch the next breakthrough the moment we cover it. When you hit that notification bell, you're choosing to be part of the generation that's learning to read messages written in ice from other star systems. On October 13th, 2024, the Atlas Survey telescope in Hawaii captured something unusual. A faint streak of light moving against the background stars, nothing remarkable at first glance. Astronomers catalogue hundreds of asteroids and comets every month. But when they calculated this object's trajectory, the numbers didn't make sense. It wasn't following an elliptical orbit around the sun like every other comet in our solar system. Instead, its path traced a hyperbola, a one-way ticket through our cosmic neighbourhood. The velocity told the full story, 87,000 miles per hour relative to the sun, far exceeding the escape velocity needed to break free from our star's gravitational grip. This wasn't one of ours. This was interstellar object number 33I/Atlas, only the third confirmed visitor from beyond our solar system ever detected by humanity. You're witnessing something extraordinarily rare. Think about the scale of what just happened. Our solar system formed 4.6 billion years ago, and in all that time, trillions of comets have orbited the sun. We've studied them for centuries, sent spacecraft to collect their dust, even landed probes on their surfaces. But interstellar objects. We didn't confirm the first one, Oumuamua, until 2017. The second, Comet Borisov, arrived in 2019. Now, just 5 years later, here's number 3. That's 3 confirmed interstellar visitors in human history. And you're living through the discovery of this one in real time. But 3I/Atlas immediately separated itself from its predecessors in a way that has scientists arguing in conference rooms and filling observation time on every major telescope they can access. When researchers at the University of Hawaii analysed the first detailed images, they measured something that made them double-check their instruments. The comet was producing a coma, that cloud of gas and dust surrounding the nucleus that extended over 10,000 kilometers into space. To put that in perspective, Earth's diameter is 12,742 kilometers. You're looking at a plume of material nearly as wide as our entire planet, erupting from an icy body probably no more than a few kilometers across. Here's where it gets strange. Most comets only develop visible tails when they venture inside the orbit of Mars, where solar radiation heats their surfaces enough to vaporize frozen materials. Halley's comet, perhaps the most famous of them all, produces a tail stretching millions of kilometers, but only when it swings close to the sun every 76 years, getting within 55 million miles of our star. At that distance, Temperatures on the comet's surface can reach 200 degrees Fahrenheit, hot enough to turn water ice directly into gas. That's normal comet behaviour. That's what we expect. 3I/Atlas was nowhere near that close. When astronomers first detected its massive plume, the comet was beyond the orbit of Jupiter, over 500 million miles from the Sun. At that distance, sunlight delivers only 4% of the energy it provides at Earth's orbit. Surface temperatures out there hover around negative 230 degrees Fahrenheit, cold enough that water ice is as hard as granite and about as likely to evaporate. Yet somehow, 3I/Atlas was venting enough material to create a plume visible across millions of miles of space. Dr. Darrell Seligman from Cornell University, who led one of the first detailed studies of the object, put it bluntly in his research team's initial report. We are seeing activity at a heliocentric distance where cometary activity should essentially be dormant. Whatever mechanism is driving this outgassing, it cannot be explained by solar heating alone. When scientists say something cannot be explained by their standard models, you know they've encountered something genuinely puzzling. The discovery triggered an urgent scramble among astronomers worldwide. Interstellar objects don't linger. They're moving too fast, and they're not coming back. Oumuamua blazed through our solar system in 2017 and disappeared before scientists could organise detailed follow-up observations, a missed opportunity that still frustrates researchers. They had maybe 2 months of usable data before it became too faint to study. Comet Borisov gave them more time, allowing observations over nearly a year, but it too eventually faded beyond detection as it raced back toward interstellar space. Now, here was 3I/Atlas, and the astronomical community wasn't going to let this one slip away without answers. Within days of the discovery announcement, observation proposals flooded into facilities operating the world's most powerful telescopes. The Hubble Space Telescope reoriented to capture high-resolution images. Ground-based observatories in Chile, Hawaii, and the Canary Islands added 3I/Atlas to their nightly target lists. The James Webb Space Telescope, humanity's newest eye on the cosmos, scheduled infrared observations to analyse the chemical composition of the plume. Every data point mattered because everyone understood the stakes. This comet was already moving away from the Sun at over 24 miles per second, and in a few months it would be too distant and too dim to study effectively. The window was closing fast. What makes your heart race about this? Is it the fact that this object travelled through interstellar space for potentially millions of years before gravity happened to steer it through our solar system? Or is it knowing that right now, as you're hearing this, telescopes are gathering light that left this comet hours ago, light carrying information about materials that formed around another star? But here's what's truly keeping astronomers up at night: that 10,000 kilometre plume isn't just big, it's impossible according to everything we know about how comets work. And the explanation scientists eventually pieced together doesn't just solve the mystery of 3I/Atlas. It opens a window into the nature of planetary systems across the galaxy, revealing the composition of worlds orbiting stars so distant that their light takes years to reach us. To understand what makes this plume so baffling, though, you first need to know what separates an interstellar intruder from the thousands of comets and asteroids that belong to our own solar system. Picture our solar system as a neighbourhood, with the Sun at its centre and planets arranged in predictable orbits like houses on curved streets. Every asteroid in the main belt between Mars and Jupiter, every comet in the distant Oort cloud, every chunk of ice in the Kuiper belt beyond Neptune, they all follow the same fundamental rule. They're trapped in elliptical orbits around the Sun. Gravity bound them to our star 4.6 billion years ago, and gravity keeps them circling. Some orbits are nearly circular like Earth's, others are wildly elongated. like comets that swing close to the Sun and then retreat beyond Pluto for centuries. But they always come back. That's what defines a solar system object. It's gravitationally committed to the Sun for the long haul. Interstellar objects don't play by those rules. They're not orbiting, they're escaping. When astronomers plot the trajectory of something like 3/Atlas, they're looking at the shape of its path through space. And that shape tells them everything. A bound orbit traces an ellipse, a closed loop. An escape trajectory traces a hyperbola, an open curve that comes in, whips around the Sun using its gravity as a slingshot, and shoots back out into the galaxy, never to return. The mathematics are unforgiving. If an object's velocity exceeds the escape velocity at its distance from the Sun, it's gone forever. For 3/Atlas, the numbers are crystal clear. At its closest approach to the Sun, called perihelion, it will pass within about 1.1 astronomical units, just slightly farther than Earth's orbit. At that distance, escape velocity is roughly 26 miles per second. You need to be moving faster than that to break free. 3/Atlas is travelling at over 30 miles per second relative to the Sun. It's not even close to being captured. It's blazing through our solar system on a trajectory that will carry it back into the space between stars. And no force in our neighbourhood is strong enough to stop it. But velocity alone doesn't prove interstellar origin. After all, couldn't this just be a comet from the outer reaches of our own solar system that got flung inward by a gravitational encounter with Jupiter or Neptune, picking up enough speed to escape? That happens sometimes. Comets get ejected from the solar system all the time when they wander too close to a giant planet. The answer lies in the direction it came from and the energy of its orbit. When astronomers traced 3/Atlas's path backward through time, running the orbital calculations in reverse, they found that it entered our solar system from the direction of the constellation Triangulum, approaching from above the plane where most planets orbit. More importantly, its excess hyperbolic velocity, the speed it would still have even at infinite distance from the Sun, is about 7 miles per second. That's the speed it had before the Sun's gravity started accelerating it inward. No object that formed in our solar system would have that kind of velocity relative to the Sun unless something catastrophic launched it. And when you check the timing and direction, there's no recent planetary encounter that could account for it. The only explanation that fits is that 3/Atlas was already moving through interstellar space with that velocity when it happened to wander into the Sun's gravitational influence. Think about the journey this object has been on. The Milky Way galaxy rotates, and stars drift relative to one another as they orbit the galactic centre. Our Sun moves through space at about 514,000 miles per hour, relative to the local standard of rest, the average motion of nearby stars. Other stars have their own velocities, slightly faster or slightly slower, creating relative motions between stellar systems. When a comet gets ejected from another star's planetary system, it becomes a wanderer, drifting through the interstellar void at whatever velocity it inherited from its home system, plus the kick it received during ejection. For 3/Atlas, that journey likely lasted millions of years. Space is incomprehensibly vast. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away, about 25 trillion miles. Even moving at 7 miles per second, it would take over 100,000 years to cross that distance. Scientists don't yet know exactly which star system ejected 3/Atlas, but they can make educated guesses based on its trajectory and velocity. Dr. Marco Micheli from the European Space Agency's Near-Earth Object Coordination Centre ran simulations tracing possible origin points and noted in his analysis that, given the object's velocity vector and accounting for galactic motion, potential parent systems lie within a radius of several hundred light-years, meaning this comet has been travelling through interstellar space for anywhere from several 100,000 to several million years. Can you imagine that an object drifting alone in the freezing darkness between stars for longer than modern humans have existed on Earth? Its surface bombarded by cosmic rays, its temperature barely above absolute zero. Then, by pure chance, its path intersects with our solar system's gravitational sphere of influence. The odds of this happening are astronomically small, which is exactly why we've only confirmed 3 interstellar visitors despite watching the skies for decades. But here's what makes 3 I/Atlas even more fascinating than just being an interstellar traveller's chemical signature. When spectroscopes analysed the light reflecting off its coma, that cloud of venting gas, they detected something specific. The spectrum showed strong absorption features consistent with carbon monoxide and molecular nitrogen, materials that sublimate at extremely low temperatures compared to water ice. On Earth, nitrogen becomes a liquid at negative 320 degrees Fahrenheit and freezes solid at negative 346 degrees. These are materials that remain frozen even in the outer reaches of planetary systems, far from the warmth of any star. The presence of nitrogen ice is your first major clue. It tells you that 3 I/Atlas likely formed in the outer regions of its home planetary system, perhaps in a zone equivalent to our Kuiper belt or even farther out. Planets like Neptune and Pluto have nitrogen ice on their surfaces because they orbit in the frozen outer darkness where such materials can remain stable. If 3 I/Atlas is rich in nitrogen, it's essentially carrying a sample of the conditions in the outer reaches of an alien planetary system, a system you'll never visit, orbiting a star whose light you've probably never seen, but whose chemical fingerprints just arrived at your doorstep. That chemical composition is about to become crucial, because it holds the key to explaining that impossible 10,000 kilometer plume. But to understand why this plume is such a problem, why it violates everything scientists thought they knew about comet behaviour, you need to see just how extreme and unexplainable this eruption really is. Let's put that 10,000 kilometer plume into proper perspective, because the numbers alone don't capture just how bizarre this situation really is. When comet 67P/Churyumov-Gerasimenko, the comet that the European Space Agency's Rosetta mission orbited and studied for 2 years, approached the Sun, in 2015 it developed a coma roughly 130 kilometers across at its closest point. That's when it was within 1.2 astronomical units of the Sun, almost exactly the same distance where 3 I/Atlas currently sits. At that range, sunlight was intense enough to heat 67P's surface to around negative 94 degrees Fahrenheit in the warmest spots, triggering jets of water vapour and carbon dioxide that sprayed several hundred meters per second from active regions on the nucleus. Scientists watching from the Rosetta spacecraft documented exactly how this process worked. Solar radiation warmed the surface. Heat conducted slowly into the subsurface ice. Pressure built beneath a thin crust, and eventually the gas burst through weak points, creating those dramatic jets. But 67P's coma, even at peak activity, was roughly 75 times smaller than what you're seeing with 3 I/Atlas. And here's the critical difference: 67P was much closer to the Sun during that active phase, receiving significantly more solar energy. When 3 I/Atlas first showed its massive plume, it was beyond Jupiter's orbit at 5.4 astronomical units, where solar radiation is 29 times weaker than at Earth's distance. The math simply doesn't work. To generate a plume this enormous at that distance using only solar heating would require the comet to have an impossibly large surface area actively venting, or the ice would need to sublimate with an efficiency that breaks the laws of thermodynamics. Dr. Jane Liu from the University of Oslo, who has spent decades studying comets and Kuiper belt objects, reviewed the initial observations of 3 I/Atlas and published a commentary noting, The scale of outgassing we're observing is inconsistent with solar-driven sublimation models at this heliocentric distance. We're looking at a mass loss rate on the order of 100 kilograms per second, producing a coma that rivals what we see from much larger comets at perihelion. Something else is powering this. 100 kilograms per second. That's 220 pounds of material being ejected into space every single second, 8.6 tons per day. For comparison, Comet Hale-Bopp, one of the brightest comets of the 20th century, lost material at about 250 kilograms per second, but that was when it passed within 0.9 astronomical units of the Sun, 6 times closer than 3I/Atlas. You're watching a comet produce nearly half the outgassing rate of Hale-Bopp while receiving only a fraction of the solar energy. The size of the plume creates another problem that makes this whole situation even stranger. Gas molecules don't just stay together in a neat cloud after they leave the comet's surface. They're travelling at hundreds of meters per second, and they disperse rapidly as they move outward. For a plume to remain visible across 10,000 kilometers, you need a sustained, powerful source continuously replenishing it. Think of it like a fountain. The water you see arcing through the air isn't the same water. Molecules from second to second. Fresh water constantly shoots up from below to maintain the spray. Similarly, that 10,000 kilometer coma means gas is actively erupting from 3I/Atalus's nucleus at rates high enough to replace material that's constantly expanding and dissipating into space. Hubble Space Telescope observations captured this in stunning detail. High-resolution images taken over several days showed the coma wasn't static, it was dynamic, with brightness variations suggesting periodic bursts of activity. In one observation sequence from late October 2024, astronomers measured the expansion velocity of material in the coma at approximately 0.3 kilometers per second, about 670 miles per hour. At that speed, gas molecules travel the full 10,000 kilometer width of the coma in roughly 9 hours. But the coma remained prominent for weeks. That's continuous outgassing on a massive scale, maintained day after day despite the comet being in a region of space where comets are supposed to be dormant. Here's a question for you if you're an astronomer staring at this data. What would your first instinct be? Where would you look for an explanation? Most scientists started with the obvious suspects. Maybe 3I/Atlas had recently passed closer to the Sun earlier in its trajectory, warming its interior, and now that stored heat was slowly leaking out, driving delayed outgassing. Comets can retain heat in their interiors for weeks or months after perihelion. We've seen that with several short-period comets that remain active even as they move back to the outer solar system. But when researchers traced 3I/Atlas's orbit backward, they found it had been inbound, approaching the Sun from interstellar space. It hadn't made a close approach yet. There was no recent perihelion passage to store heat. The comet was actually getting closer to the Sun for the first time in millions of years, which meant it should be getting more active as it approached. Not already erupting at peak levels while still in the cold outer system. Another hypothesis may be the comet's nucleus was unusually dark, with a surface that absorbed solar radiation more efficiently than typical icy bodies. Darker surfaces heat up faster because they reflect less light, but spectroscopic analysis showed 3I/Atlas had an albedo, a measure of reflectivity around 4 to 6%. Similar to other comets. Nothing exceptional there. Even if it were perfectly black, absorbing 100% of incoming sunlight. The energy available at 5 astronomical units still wouldn't be sufficient to explain this level of activity. What about a collision? Could 3I/Atlas have smashed into a small asteroid or another comet during its journey through the solar system, shattering part of its nucleus and exposing fresh ice that's now rapidly sublimating? It's not impossible, space isn't completely empty. And impacts happen. but collisions between objects in the vastness of the solar system are exceptionally rare, and when they do occur, they typically produce distinctive debris clouds and dust patterns. Multiple telescopes scrutinize 3I/Atlas for any sign of fragmentation asymmetric dust trails, secondary condensations in the coma, brightness changes consistent with nucleus breakup. They found none. The nucleus appeared intact, with outgassing that looked controlled and localized rather than the chaotic spray you'd expect from a catastrophic impact. Then there was the truly exotic idea that kept appearing in internet discussions and even in a few scientific conference-side conversations. Could this be an artificial object after all? Oumuamua sparked intense debate when some researchers suggested its unusual acceleration might indicate artificial origins, a light sail pushed by radiation pressure, or even a probe from another civilization. Could 3I/Atlas be venting propellant, deliberately maneuvering through our solar system? The scientific community's response to that speculation was swift and clear. Dr. Michelle Bannister from the University of Canterbury in New Zealand, who studies trans-Neptunian objects and interstellar visitors, addressed this directly. While we should remain open to unexpected discoveries, nothing about 3I/Atlas's behaviour requires exotic explanations. We're seeing comet activity complex, yes, and not immediately explained by our simplest models, but still consistent with natural volatile sublimation under the right conditions. The challenge isn't whether this is natural, it's identifying which volatiles and which heating mechanisms are responsible. So, if solar heating isn't enough, if there's no recent perihelion, no collision, and no credible evidence of artificial origins, what's left? The answer lies in the specific materials 3I/Atlas is made of, and in a discovery scientists made on a frozen world at the edge of our own solar system that completely changed how we think about ice. July 14th, 2015, NASA's New Horizons spacecraft screamed past Pluto at 31,000 miles per hour, coming within 700-800 miles of the dwarf planet's surface. After a 9.5-year journey across the solar system, the probe had exactly one shot to capture data during its brief flyby, cameras clicking, spectrometers analysing, instruments recording everything they could in those precious few hours. When the first high-resolution images downloaded back to Earth over the following days, scientists sat in stunned silence. They'd expected a dead, cratered world, frozen solid for billions of years. Instead, they were looking at something geologically active, with smooth plains that couldn't be more than 100 million years old practically yesterday in planetary terms, and towering mountains made of water ice rising 11,000 feet above the surface. But the real revelation was a feature they named Sputnik Planitia, a vast, heart-shaped plain spanning 600 miles across. This wasn't water ice. Spectroscopic analysis revealed it was almost pure nitrogen ice, stretching as far as the instruments could see, divided into irregular polygonal cells like a cracked eggshell. Each cell was roughly 10 to 25 miles across, and the boundaries between them showed where warmer nitrogen was slowly convecting upward from below, creating a process similar to lava lamps, except the lava was frozen nitrogen at negative 390 degrees Fahrenheit, and the timescale was measured in hundreds of thousands of years. The scientists realized they were witnessing something profound. Nitrogen ice, even at temperatures barely above absolute zero, isn't completely inert, it's volatile. It sublimates, transforms directly from solid to gas at temperatures where water ice would be as stable as concrete. On Pluto, atmospheric pressure is about 100,000 times lower than Earth's, and surface temperatures average around negative 380 degrees Fahrenheit. Under those conditions, nitrogen ice can exist as a solid, but it's perpetually on the edge of sublimating. Seasonal variations in sunlight, even as faint as it is at 40 times Earth's distance from the Sun, are enough to trigger cycles of sublimation and condensation. During Pluto's 248-year orbit, nitrogen ice evaporates from one hemisphere and condenses on the other as seasons change, redistributing literally billions of tons of material. Dr. Alan Stern, principal investigator for the New Horizons mission, described the discovery in a press conference. What we found on Pluto fundamentally changed our understanding of how volatile ices behave in the outer solar system. Nitrogen is active at temperatures and pressures where we thought everything would be geologically dead. It's teaching us that ice isn't just ice. Different materials behave radically differently depending on their composition and environment. That lesson from Pluto became the key to unlocking the mystery of 3I/Atlas. Remember that spectroscopic detection of nitrogen in the comet's coma? That wasn't just an interesting detail, it was the smoking gun. If 3I/Atlas has a nucleus rich in nitrogen ice, you're no longer dealing with a typical comet dominated by water ice. You're dealing with something that behaves fundamentally differently, something that can remain active at distances from the Sun where water ice comets go dormant. Think about the properties that make nitrogen special. Water ice sublimates at temperatures above 32 degrees Fahrenheit at Earth's atmospheric pressure. But in the near vacuum of space, it needs temperatures around -40 degrees or warmer to sublimate at significant rates. Carbon dioxide dry ice sublimates at -109 degrees Fahrenheit in space. But nitrogen, it sublimates at -346 degrees Fahrenheit. That's a difference of over 200 degrees compared to water. A comet made primarily of nitrogen ice can be active at distances where water-dominated comets are completely frozen solid. Now, scientists had a working hypothesis. If 3I/Atlas formed in the outer reaches of its home planetary system, similar to how objects form in our Kuiper belt, it could be composed primarily of nitrogen ice with smaller amounts of carbon monoxide, methane, and other ultra-volatile materials. When this comet drifted through interstellar space for millions of years, cosmic rays would have been constantly bombarding its surface, breaking apart molecules and creating a layer of radiation-processed crust. But beneath that crust, pristine nitrogen ice would remain, insulated and frozen at the ambient temperature of interstellar space about -455 degrees Fahrenheit, only 5 degrees above absolute zero. Then 3I/Atlas entered our solar system. As it fell inward toward the Sun, even the faint increase in solar radiation would start to warm its surface. At the distances we're talking about 5 to 6 astronomical units, the heating is gentle, but it's enough. Nitrogen ice doesn't need much. Even warming from -455 degrees to -380 degrees provides sufficient energy for sublimation to begin. Cracks in that radiation-processed crust, thermal stresses from uneven heating, or simply the accumulated effect of weeks of exposure could create venting pathways. Once gas starts escaping, it carries away more heat, cooling the immediate area but also creating pressure beneath the surface that can blow away more crust material, exposing fresh ice and accelerating the process. Laboratory experiments have actually tested this scenario. Researchers at institutions like NASA's Jet Propulsion Laboratory and the Planetary Science Institute have built vacuum chambers where they can simulate the conditions of deep space. They place samples of nitrogen in carbon monoxide ice and mixtures of volatiles in these chambers, cool them to the temperatures found beyond Jupiter's orbit, and then gradually warm them with calibrated heat lamps mimicking solar radiation at various distances. The results are striking. Nitrogen ice begins vigorous sublimation at temperatures where water ice shows no activity whatsoever. Doctor, Yanga Fernandez from the University of Central Florida, who has conducted these types of experiments, explained the findings. When you expose nitrogen ice to the thermal environment at 5 astronomical units, you get sublimation rates orders of magnitude higher than water ice at the same distance. The vapor pressure of nitrogen ice is so much higher that even small temperature increases drive substantial mass loss. If 3i/Atlas is nitrogen-rich, its behaviour makes perfect sense. But here's where the story gets even more interesting, because nitrogen ice alone still doesn't fully explain the power behind that 10,000 kilometre plume. You need something more, an additional energy source, or a mechanism that concentrates the outgassing into powerful jets rather than a gentle, diffuse seeping of gas. The answer to that puzzle involves understanding exactly how a comet's interior can become a pressure vessel, building up force until it erupts with explosive violence. Have you ever shaken a bottle of soda and then opened it? That's a crude analogy for what happens inside an active comet nucleus, except instead of carbonation, you're dealing with sublimating ice, and instead of a few seconds of fizzing, the process can sustain itself for weeks. The physics of how gas pressure builds beneath an icy crust and then escapes through vents is about to reveal why 3i/Atlas is spraying material with such tremendous force. Imagine you're standing inside a comet nucleus, not the romantic, glowing tail we see from Earth, but the actual solid body, the dirty snowball at the heart of it all. You're surrounded by ice, but this isn't the clear, crystalline ice you find in a glacier. This is a chaotic mixture nitrogen ice, carbon monoxide ice, maybe some water ice, all jumbled together with dust grains, organic compounds, and rocky particles accumulated over billions of years. The structure is porous, riddled with tiny voids and cracks like a frozen sponge. Above you, maybe just a few meters overhead, is the surface a dark crust of dust and radiation-damaged material that's been baked by cosmic rays during the comet's million-year journey through interstellar space. Now, the comet enters a solar system. Sunlight faint, but present begins warming that surface layer. Heat conducts slowly downward through the porous material, a process that might take hours or days to penetrate just a few centimeters. When that heat reaches the subsurface nitrogen ice, something critical happens. The ice begins to sublimate, transforming directly from solid to gas without melting, unlike water, which expands only about 1/700 times when it vaporizes. Nitrogen expands roughly 700 times its solid volume when it becomes gas at the low pressures found in space. That's an enormous expansion ratio, and it happens fast. Here's where the physics gets dramatic. The gas has to go somewhere, but it's trapped beneath that crusty surface layer. Pressure starts building in the pores and cracks of the subsurface ice. As more nitrogen sublimates, the pressure increases exponentially. Think of it like inflating a balloon inside a box at first. The balloon expands easily, but as it fills the available space, the pressure against the walls rises sharply. Inside the comet, gas pressure in the subsurface voids can reach several times the ambient pressure of the surrounding space, which essentially means going from nearly zero pressure to measurable force concentrated in confined areas. Eventually, something gives. The weakest point in that surface crust may be a pre-existing crack, maybe a thin spot where the dust layer is only millimeters thick ruptures. Gas explodes outward like uncorking a champagne bottle, carrying with it dust particles, ice fragments, and more sublimating nitrogen. The velocity of this jet can reach 300 to 500 meters per second, up to 100 miles per hour, fast enough to escape the comet's weak gravity and stream into space. And here's the beautiful part: once that vent opens, it creates a feedback loop. The escaping gas cools the immediate area through a process called adiabatic expansion, but it also removes the insulating crust, exposing fresh nitrogen ice directly to sunlight. That fresh ice sublimates even faster, maintaining the jet's flow. The European Space Agency's Rosetta mission gave us front-row seats to this process when it orbited Comet 67P for 2 years. High-resolution cameras captured jets erupting from specific locations on the nucleus. Some lasting for hours, others pulsing on and off as pressure built and released. Scientists measured the gas velocity, the dust-to-gas ratio, the temperature variations on the surface. In one particularly revealing observation sequence from August 2015, instruments detected a sudden burst where the outgassing rate spiked by a factor of 3 in less than an hour. Post-analysis showed that a cliff collapse had exposed fresh ice beneath, triggering an intense sublimation event. Within days, the newly exposed area had darkened again as dust settled back down, and the outgassing diminished, but not before millions of kilograms of material had been ejected. For 3I/Atlas, this process operates on a much larger scale because of nitrogen's extreme volatility. Dr. Dennis Bodowitz from Auburn University, who specializes in cometary outgassing physics, modeled the gas dynamics for nitrogen-rich interstellar objects and found something striking. The sublimation rate of nitrogen ice at 5 astronomical units can be 10 to 100 times higher than water ice at the same distance. When you factor in the lower molecular weight of nitrogen, 28 atomic mass units, compared to 18 for water, the gas molecules also move faster, carrying more kinetic energy. This creates jets with higher velocities and greater mass flux than we're accustomed to seeing in water-dominated comets. Let's talk about what that means for the 10,000 kilometer plume. When gas erupts from the nucleus at 400 meters per second, it carries dust and ice particles with it. Initially, everything moves together in a collimated jet, a focus stream, like water from a high-pressure hose. But as the material expands into the near vacuum of space, several things happen. The gas molecules, moving at hundreds of meters per second, spread outward in all directions. Dust particles, which have mass and momentum, continue forward but gradually slow down due to the tiny drag from the gas. Ice particles sublimate as they travel, feeding more gas into the coma. Sunlight scatters off the dust, making the plume visible from Earth. The size of the resulting coma depends on how fast material is being ejected, how long the outgassing continues, and how the gas and dust disperse. For 3I/Atlas, calculations suggest the nucleus, probably just 1 to 2 kilometers in diameter, is losing about 100 kilograms of material every second. Over the course of a day, that's 640 kilograms, nearly 10 tons. Over a week, roughly 60 tons. That might not sound like much for an object that could weigh tens of billions of kilograms. But remember, this is all coming from active areas on the surface, maybe covering only a few % of the total nucleus area. The rest is likely still insulated by that dusty crust. What powers this continuous outgassing for weeks on end? Here's where things get really interesting. Nitrogen ice has a property called high thermal inertia, meaning once it starts sublimating, it can sustain that process with relatively little additional energy input. The phase change itself from solid to gas absorbs heat, cooling the surface, but the pressure-driven venting exposes fresh material faster than the surface can refreeze. It's a self-perpetuating cycle as long as sunlight continues to provide even minimal heating. But there's another factor scientists are considering: internal heat sources. Comets aren't completely cold inside. They contain trace amounts of radioactive isotopes, aluminum-26, potassium-40, uranium-238 incorporated, when the comet formed from the primordial nebula around its parent star. These isotopes decay over millions of years, releasing heat. The amount is tiny, but in the insulating environment of a porous ice ball, that heat can accumulate over time, gradually warming the interior. A comet that's been drifting through interstellar space for 1,000,000 years might have a core several degrees warmer than its surface. Not from any external source, but purely from the slow radioactive decay happening within. When such a comet enters a solar system and external heating begins, that stored internal warmth creates a thermal gradient warmer inside, cooler outside. This gradient can drive sublimation from below, where gas pressure builds in the interior and forces its way outward through cracks and vents. Dr. Kathleen Mant from Johns Hopkins Applied Physics Laboratory, who has studied cometary thermodynamics, noted in her research for volatile-rich bodies like nitrogen ice comets. Even a few degrees of internal warming can significantly enhance outgassing rates. The combination of external solar heating and internal radiogenic heat creates ideal conditions for sustained, vigorous activity at heliocentric distances where water ice comets would be dormant. Can you picture it now? A comet nucleus spinning slowly through space, surface temperature hovering around negative 380 degrees, but inside, cracks and voids filled with nitrogen gas at slightly elevated pressure, constantly seeking escape routes, finding them, erupting in focused jets that blast material thousands of miles into space. That's your 10,000 kilometer plume, not a passive cloud, but an active dynamic eruption powered by the physics of volatile sublimation. Yet even with this understanding of nitrogen ice behavior and internal heating, there's still a piece of the puzzle that doesn't quite fit, because 3I/Atolase isn't just venting gas, it's accelerating. Observations have detected something scientists call non-gravitational acceleration, where the comet's trajectory is being altered by the force of its own outgassing. And that discovery opens up a whole new dimension to this story. Newton's laws tell us that every action has an equal and opposite reaction. When a rocket engine fires, hot gas blasts out the back at tremendous velocity, and the rocket experiences thrust in the opposite direction, propelling it forward. The same principle applies to comets, except they're not designed for propulsion, they're just chunks of ice venting gas as they heat up. But that venting still creates force, and force changes motion. When astronomers calculate a comet's trajectory using only gravitational influences the sun's pull, the planet's gravitational tugs, and then compare those predictions to actual observations, they sometimes find discrepancies. The comet isn't quite where it should be. It's been pushed slightly off course by the force of its own outgassing. Scientists call these trajectory changes non-gravitational accelerations, and they're a telltale sign of active venting. For most comets, these effects are tiny, measured in fractions of a millimeter per second squared, barely detectable even with precise observations, but they're real, and they've been documented for decades. Comet Halley, for instance, arrives at perihelion several days earlier or later than purely gravitational calculations would predict because centuries of outgassing have nudged its orbit. Scientists have to account for these non-gravitational forces when predicting when and where comets will appear. It's one of the reasons comet orbit predictions sometimes miss the mark. There's a rocket engine effect we can't perfectly model because we don't know exactly how strong the outgassing will be or which direction the jets will point. Now apply that concept to 3I/Atlas. When researchers at the Minor Planet Center and other orbital dynamics groups began tracking the comet's position over multiple nights, they noticed something immediately. The trajectory wasn't purely gravitational. The comet was accelerating in a direction that couldn't be explained by the sun's gravity or the influence of any planet. Detailed analysis showed a non-gravitational acceleration component of approximately 1.2 millimeters per second squared, directed roughly away from the sun, consistent with a sustained outgassing force pushing the comet like a slowly firing rocket engine. That might sound minuscule. After all, 1.2 millimeters per second squared is about 12,000 times weaker than Earth's gravity. But in the frictionless vacuum of space, even tiny forces accumulate over time. After 1 hour, that acceleration changes the comet's velocity by 4.3 meters per second, about 10 miles per hour. After 1 week, it's altered the velocity by over 700 meters per second, more than 500 miles per hour. After a month, the comet's trajectory has been perturbed by thousands of kilometers compared to where it would have been if only gravity were acting on it. For an object travelling at interstellar velocities, this is a measurable, significant effect. Dr. David Farnokia from NASA's Center for Near-Earth Object Studies ran the orbital dynamics calculations for 3Y/Atlas and published the findings. The non-gravitational acceleration we're detecting is among the strongest we've observed for any comet at this heliocentric distance. It's consistent with asymmetric outgassing producing thrust, and the magnitude correlates well with the observed gas production rates. This object is effectively propelling itself through the solar system via natural venting processes. Here's where the story connects directly to one of the most controversial interstellar objects ever detected, Oumuamua. When that cigar-shaped visitor passed through our solar system in 2017, astronomers noticed it was also experiencing non-gravitational acceleration. It was speeding up as it moved away from the Sun, gaining velocity that couldn't be attributed to gravitational effects. The numbers were small but undeniable. Oumuamua was being pushed by something. That observation sparked an intense scientific debate. Dr. Avi Loeb from Harvard University proposed that the acceleration could be evidence of an artificial light sail, a thin, reflective sheet pushed by sunlight, a technology that could theoretically be used for interstellar travel by advanced civilizations. His argument was that Oumuamua showed no detectable outgassing, no visible coma or tail, yet was still accelerating. If it wasn't venting gas, what was pushing it? A light sail would experience radiation pressure from sunlight without producing any gas emissions. The hypothesis was bold, and it generated headlines worldwide. The scientific community largely pushed back, offering alternative explanations. Maybe Oumuamua was venting gas, but the composition was hydrogen, which is invisible to most detection methods and wouldn't produce a visible coma. Or perhaps it was venting from a small active area that telescopes simply couldn't resolve. Or the acceleration was due to outgassing of some other exotic volatile that doesn't create detectable dust clouds. The debate highlighted a fundamental challenge when you're observing an object millions of miles away for only a few weeks before it disappears forever. You're working with incomplete data. You're making educated guesses based on limited evidence. 3I/Atlas doesn't have that ambiguity. You can see the outgassing. The 10,000 kilometer plume is visible proof that gas is erupting from the nucleus, and the non-gravitational acceleration perfectly matches what you'd expect from that venting. There's no need to invoke exotic explanations or artificial origins. This is natural rocket propulsion powered by sublimating nitrogen ice. The physics are straightforward. Gas leaves the nucleus at high velocity in one direction, and the nucleus experiences thrust in the opposite direction. Multiply the mass flow rate 100 kilograms per second by the gas velocity 400 meters per second, and you get the thrust force. The math checks out. But here's what makes this particularly fascinating: the direction and variability of the thrust. Comets don't vent uniformly from all sides. They typically have active regions, specific areas on the surface where jets form, often clustered near the neck of irregularly shaped nuclei or in regions where the crust is thinner. As the comet rotates, these active regions turn toward and away from the Sun, creating a pulsing pattern of outgassing. If a jet is firing from one side of the nucleus while the comet spins, the thrust vector sweeps around like a lighthouse beam, sometimes pushing the comet forward along its trajectory, sometimes sideways, sometimes backward. For 3I/Atlas, observations suggest the nucleus is rotating with a period of roughly 6 to 8 hours, meaning it completes one full rotation every 6 to 8 hours. That's relatively fast for a comet. During each rotation, the active regions cycle through day and night, heating up when facing the sun and cooling when in shadow. The outgassing intensity varies accordingly, and so does the thrust. Modelling this rotational effect is complex because you need to know the exact shape of the nucleus, the locations of active areas, the rotation axis orientation, and how all these factors change as the comet moves along its orbit. It's like trying to predict the flight path of a bottle rocket that's spinning, tumbling, and venting erratically. What's the real-world impact of this thrust? Think about it this way: if 3I/Atlas is being pushed by its own outgassing, that means its exit trajectory from our solar system will be slightly different than if it were just coasting on gravity alone. The non-gravitational acceleration is nudging it onto a new path through interstellar space. When this comet leaves our neighbourhood and continues its million-year journey between the stars, it'll be heading in a slightly altered direction compared to where it came from. Over millions of years, that small change compounds. The next star system it encounters, if it encounters one at all, might be completely different than if the outgassing hadn't occurred. In a sense, 3I/Atlas is steering itself, albeit unintentionally. It's a natural spacecraft experiencing course corrections, powered by the ice it's losing to space. And that raises a profound question: if comets can alter their own trajectories through outgassing, what does that tell us about the journeys these objects take through the galaxy? How many have been redirected by their own activity, sent on paths they wouldn't have followed otherwise? The answers to those questions hinge on understanding not just how nitrogen ice behaves on 3I/Atlas, but what that nitrogen reveals about the alien planetary system. This comet came from a system whose secrets are written in the chemical composition of this frozen messenger. Every comet is a time capsule. The ice and dust locked inside these ancient bodies formed billions of years ago in the planetary disk surrounding a young star, the swirling cloud of gas and dust that eventually coalesced into planets, moons, asteroids, and comets. The materials preserved in comets represent the original building blocks of planetary systems, largely unchanged since the era of formation. When you analyse the chemical composition of a comet, you're essentially reading a recipe, the ingredients that were available in that particular stellar neighbourhood when worlds were being born. For comets in our solar system, we've learned a tremendous amount from this chemical detective work. Missions like Rosetta, Stardust, and Deep Impact have directly sampled cometary material or analysed their spectra in detail. We know that most comets contain water ice as their primary volatile component, along with carbon dioxide, carbon monoxide, methane, ammonia, and a complex mixture of organic molecules, some as simple as formaldehyde, others as intricate as amino acids, the building blocks of proteins. The ratios of these materials tell us about the temperature and pressure conditions in the outer solar nebula 4.6 billion years ago, where these comets formed beyond the orbit of Neptune in the cold, dark reaches where sunlight barely reached. But 3I/Atlas didn't form in our solar system. It condensed from the planetary disk of another star, in conditions we can only infer. And here's what makes that so exciting: when spectroscopes trained on 3I/Atlas analysed the light passing through its coma, they detected something that immediately set it apart from typical solar system comets. The dominant volatile wasn't water, it was nitrogen, with significant amounts of carbon monoxide. That chemical signature tells a very specific story about where and how this comet formed. Dr. Martin Cordner from NASA's Goddard Space Flight Center led a spectroscopic study using radio telescopes to measure emission lines from molecules in the coma. His team detected carbon monoxide at levels suggesting it comprises roughly 15 to 20% of the volatile content, far higher than typical solar system comets, where carbon monoxide usually accounts for less than 1%, nitrogen, while harder to detect directly because it doesn't emit strongly at visible wavelengths, appeared to be even more abundant based on the overall gas production rates and the molecular ratios observed. Cordner's analysis concluded the composition we're measuring is consistent with formation in an extremely cold environment, likely in the outer regions of a planetary system where temperatures remained below 30 Kelvin, that's negative 405 degrees Fahrenheit, throughout the system's early history. Think about what that means. In our solar system, the region where nitrogen ice can remain stable during planetary formation is far beyond Neptune, out in the Kuiper Belt and Oort cloud, where temperatures during the solar system's youth dropped low enough for nitrogen to freeze solid before being incorporated into comets. Objects forming closer in, where water ice condenses but nitrogen remains gaseous, become water-rich comets like the ones we're most familiar with. The abundance of nitrogen in 3a/Atlas suggests it formed in a zone equivalent to or even farther out than our Kuiper Belt, a region at least 30 to 50 astronomical units from its parent star. But which star? Where did this comet come from? That's a question astronomers have been trying to answer since the moment they calculated its trajectory. By tracing 3a/Atlas's path backward through space and accounting for the gravitational influence of every star within hundreds of light years, researchers can narrow down possible origin points. The calculations are fiendishly complex because stars aren't stationary. They're all moving through the galaxy at different velocities, orbiting the galactic center on timescales of hundreds of millions of years. To trace a comet's origin, you need to model not just where stars are now, but where they were millions of years ago when the comet was ejected. Preliminary studies suggest 3a/Atlas likely originated from a star system within 150 to 300 light-years of the Sun. That's our cosmic neighbourhood, in galactic terms a region containing thousands of stars, many of them similar to our Sun, some larger, some smaller, some in binary pairs. The exact parent star remains uncertain, but the possibilities are tantalising. It could have come from a system around a G-type star like our Sun, where a planetary architecture similar to ours exists. Or it might have originated around a K-type star slightly smaller and cooler than the Sun, but still capable of hosting planets and generating enough warmth in their inner regions to create temperature gradients that form diverse comet populations. Here's where the nitrogen abundance becomes even more revealing. Nitrogen is the 7th most abundant element in the universe, and it's a key component of planetary atmospheres. Earth's atmosphere is 78% nitrogen. Titan, Saturn's largest moon, has an atmosphere that's 98% nitrogen thicker than Earth's, despite Titan's smaller size. Triton, Neptune's largest moon, has nitrogen ice covering its surface and a thin nitrogen atmosphere. The presence of nitrogen-rich comets like 3a/Atlas suggests that its home system likely has or had large icy worlds in the outer regions where nitrogen ice could accumulate and eventually get incorporated into comets. Dr. Amaya Morrow-Martin from the Space Telescope Science Institute, who studies planetary system architectures, explained the implications. When we detect a nitrogen-rich interstellar comet, we're essentially sampling the outer reaches of an exoplanetary system. This tells us that system has a cold outer zone, probably with icy giant planets or a population of Pluto-like dwarf planets where nitrogen ice is stable. It's indirect evidence of planetary architecture we could never observe directly because these outer regions are too faint and distant to image with current telescopes. Can you imagine that you're analysing the chemical fingerprints of an alien world you'll never see, orbiting a star whose name you don't know, existing in a planetary system that formed billions of years ago? The ice venting from 3a/Atlas, right now as it passes through our solar system, is material that condensed in the cold outer reaches of that distant system, perhaps from a disk of gas and dust surrounding a young star shortly after it ignited nuclear fusion in its core. That nitrogen was part of the nebula from which planets formed. It might have been incorporated into the atmosphere of a Neptune-like ice giant before being released back into space through collisions or atmospheric escape. It could have spent billions of years cycling through the outer system before finally being gravitationally ejected, sent on a journey through interstellar space that lasted longer than the entire history of human civilization. And now it's here, close enough for you to study. Every photon of light that scatters off the dust in that 10,000 kilometre plume, every spectral line detected by radio telescopes, every measurement of gas velocity and composition, it's all data from another star's planetary system. This is exoplanet science in its most direct form, not just detecting the faint wobble of a distant star or the subtle dimming as a planet transits in front of it, but actually analysing physical material from that system delivered right to our doorstep. The carbon monoxide detected alongside the nitrogen adds another layer to the story. Carbon monoxide ice sublimates at temperatures around -364 degrees Fahrenheit, slightly warmer than nitrogen but still extraordinarily cold. Its presence in high abundance suggests the parent system's outer regions contain significant amounts of carbon and oxygen, locked into simple molecules during the cold, early phases of planetary formation. In our solar system, carbon monoxide is found in comets, but it's typically a minor component. The fact that it's so prominent in 3a/Atlas hints that the chemistry in its home system might have been slightly different. Perhaps a higher initial abundance of carbon relative to oxygen, or different thermal processing during planet formation that favoured carbon monoxide over other carbon-bearing molecules. These aren't just abstract scientific curiosities. The chemical composition of comets influences the potential for life in a planetary system. Comets delivered vast quantities of water and organic materials to Earth during the late heavy bombardment period, billions of years ago, potentially providing the ingredients necessary for life to begin. If 3a/Atlas's home system has comets like this one, nitrogen-rich, volatile-laden icy bodies, then those comets could have delivered similar materials to planets in that system's habitable zone. Nitrogen is essential for life as we know it, a critical component of amino acids and nucleic acids. A planetary system with abundant nitrogen ice in its outer reaches has a ready reservoir of this vital element. What other secrets does 3a/Atlas carry in its frozen nucleus? What other molecules are locked in that ice? Waiting to be detected as they sublimate into the coma, scientists are racing to find out, because the opportunity won't last much longer. Time is not on anyone's side when studying interstellar objects. Unlike the thousands of asteroids and comets native to our solar system bodies we can observe year after year, waiting patiently for favourable viewing conditions or the next close approach, interstellar visitors are ephemeral. They arrive unannounced, pass through our cosmic neighbourhood in a matter of months, and vanish back into the interstellar void, never to return. The window of opportunity is brutally short, and astronomers know it. Every night of clear weather, every hour of telescope time, every spectrum captured could be the last chance to gather critical data before the object fades beyond detection. When 3a/Atlas was discovered in October 2024, the astronomical community immediately understood the stakes. Initial brightness estimates suggested the comet would remain observable for perhaps 3 to 4 months before it moved too far from Earth and the Sun. dimming below the detection threshold of even the most powerful telescopes. By late January or early February 2025, it would likely be gone from view, reduced to a faint smudge of light lost among the countless background stars, and soon after, invisible entirely. That gave researchers roughly 100 days to extract every piece of information they could from this messenger from another star system. The response was swift and coordinated. Within 48 hours of the discovery announcement, observation proposals flooded into telescope allocation committees worldwide. The Hubble Space Telescope, still operating after more than 3 decades in orbit, scheduled multiple observation windows to capture high-resolution images of the nucleus and coma structure. The James Webb Space Telescope, with its powerful infrared instruments, was redirected to analyze the thermal emission from the nucleus and detect molecular signatures invisible to optical telescopes. Ground-based facilities in Chile home to some of the largest telescopes on Earth, including the Very Large Telescope Array added 3 I/Atlas to their priority target lists. Dr. Michelle Bannister, who coordinated one of the international observation campaigns, described the urgency. "We're essentially doing triage. We have limited time and limited resources, so we have to prioritize the observations that will give us the most critical scientific return. Can we determine the nucleus size and rotation rate? Can we measure the isotopic ratios in the gas to understand formation conditions? Can we detect minor species methane, ammonia, complex organics that would tell us more about the chemistry of the parent system? Every observation has to count." The challenges are significant. 3 I/Atlas is much fainter than the bright comets that occasionally grace our skies and become visible to the naked eye. At its peak brightness, the comet reached only about magnitude 14, roughly 1/600 times too dim to see without a telescope. To put that in perspective, the faintest stars visible to the human eye under perfectly dark skies are about magnitude 6. Every 5 steps on the magnitude scale represents a factor of 100 in brightness, so magnitude 14 objects require serious optical equipment and long exposure times to detect. For detailed spectroscopy, splitting the comet's light into its component wavelengths to identify specific molecules, you need even longer exposures and larger telescopes. Weather becomes the enemy. A cloudy night at a major observatory means lost data that can never be recovered. Telescope scheduling conflicts, where multiple teams compete for the same observation windows, force difficult choices. Mechanical failures, calibration issues, even cosmic ray hits on detector arrays, any of these can corrupt data or delay observations, and all the while, 3 I/Atlas is moving farther away, fading a little more each day. Radio telescopes joined the effort, targeting molecular emission lines that reveal the comet's composition. The Atacama Large Millimeter Array in Chile, an array of 66 radio dishes working in concert, sensitive enough to detect the faint radio waves emitted by molecules in space, was directed to search for carbon monoxide, hydrogen cyanide, methanol, and formaldehyde in the coma. These molecules emit at specific radio frequencies when they're excited by solar ultraviolet light, and detecting them provides a direct census of what's venting from the nucleus. Each molecule has a unique spectral fingerprint, like a barcode that identifies it unambiguously. But even with these powerful instruments, detection limits exist. Some molecules are simply too scarce or too faint to see. Others require observation conditions, specific angles relative to the Sun, particular velocity ranges that might not align during the brief time the comet is accessible. Scientists are painfully aware that they're sampling only a fraction of what's really there. It's like trying to understand an entire ecosystem by looking at a handful of organisms collected during a brief field trip. The James Webb Space Telescope observations were particularly crucial. Webb's infrared capabilities allow it to detect the thermal glow from the nucleus itself, not just reflected sunlight, By measuring this thermal emission across multiple wavelengths, scientists can determine the nucleus temperature with precision and estimate its size. Preliminary data from Webb's near-infrared spectrograph suggested the nucleus is roughly 5 kilometers in diameter, about 1 mile across, with a surface temperature around negative 360 degrees Fahrenheit at the time of observation. That's warmer than the negative 455 degrees of interstellar space, but still cold enough that water ice would be frozen harder than steel. Webb also detected absorption features in the infrared spectrum, consistent with organic molecules, complex carbon-based compounds mixed into the ice. These organics likely formed through radiation processing during the comet's journey through interstellar space, where cosmic rays broke apart simple molecules and allowed them to recombine into more complex structures. The exact composition remains under analysis, but early indications suggest similarities to the tholins, reddish-brown organic materials found on bodies like Pluto and Titan. It's a reminder that chemistry happens even in the cold depths of space, slowly building molecular complexity over millions of years. One of the most ambitious observation attempts involved trying to detect isotopic ratios in the venting gas. Isotopes are variants of elements with different numbers of neutrons, for example. Regular nitrogen has 7 protons and 7 neutrons, while nitrogen-15 has 7 protons and 8 neutrons. The ratio of nitrogen-14 to nitrogen-15 in a comet reveals information about the temperature and environment where it formed. Different stellar environments produce different isotopic ratios, so measuring these ratios in 3I/8LS could provide clues about the characteristics of its parent star and the conditions in that system's planetary disk. However, detecting isotopes requires extremely high-resolution spectroscopy because the spectral lines from different isotopes are very close together, separated by tiny fractions of a wavelength. It's like trying to distinguish 2 musical notes that are almost the same pitch. Dr. Stephanie Millam from NASA Goddard, who led the isotopic analysis effort, explained the difficulty. We're pushing our instruments to their absolute limits. The signal-to-noise ratio is marginal, and we need long integration times to accumulate enough photons to make reliable measurements. We might get a tentative detection, or we might just get upper limits constraints on what the ratios could be. But even limits are valuable because they narrow down the possibilities. How would you feel if you were one of these astronomers, knowing that every cloudy night, every technical glitch, every missed observation opportunity is data you'll never get back? The pressure is immense. This isn't studying a planet that will be there next year, or a star that will shine for billions of years. This is a once-in-a-lifetime opportunity, literally once in human history, for this specific object to gather data from a world formed around another star. By early December 2024, about 6 weeks after discovery, the comet had already faded noticeably. Its magnitude dropped from 14 to nearly 15, a decrease in brightness of about 40%. The rate of outgassing appeared to be declining as well, as 3I/Atlas moved farther from the Sun and the solar heating diminished. Some of the more ambitious observation programs had to be scaled back or cancelled as the target became too faint for the planned integration times. The window was closing faster than hoped. Yet despite these challenges, the data collected during these intense weeks of observation represents an unprecedented treasure trove of information about an interstellar visitor. And now, as the observations wind down and scientists begin the painstaking work of analysis, the legacy of 3I/Atlas is already shaping how astronomers think about future encounters with objects from beyond our solar system. The frustration astronomers felt watching Oumuamua disappear in 2017 still lingers in the scientific community. That first confirmed interstellar visitor arrived before anyone was really prepared. By the time researchers realized what they were looking at, not just another asteroid, but something from beyond our solar system. It was already racing away from the Sun at 196,000 miles per hour. Observation windows were fleeting and the object was faint and fast-moving. Scientists scrambled to collect data, but within weeks, Oumuamua had faded beyond detection. The world's most powerful radio telescopes listened for any signal that might indicate artificial origins, but heard only silence. Optical telescopes captured what images they could, revealing an elongated shape unlike typical asteroids or comets. But the details remained fuzzy. By early 2018 it was gone, leaving behind more questions than answers and a scientific community determined not to let the next opportunity slip through their fingers. That determination gave birth to a new approach: preparedness. If interstellar objects are passing through our solar system more often than previously thought, and the discovery of 3 in just 7 years suggests they might be, then humanity needs to be ready to respond quickly when the next one arrives. The European Space Agency took this challenge seriously and designed a mission specifically for this purpose: Comet Interceptor. Launched in 2029 and currently waiting in orbit at a gravitationally stable point in space called Lagrange Point 2, about 930,000 miles from Earth. Comet Interceptor is a spacecraft with a unique mission profile. It's not heading to any specific target. Instead, it's sitting idle, instruments powered down, waiting for astronomers to discover a pristine comet, either a long-period comet making its first pass through the inner solar system, or better yet, an interstellar visitor. When that object is detected and its trajectory calculated, Comet Interceptor will receive the command to wake up, fire its engines, and intercept the target as it passes through our neighbourhood. The spacecraft carries 3 separate probes that will split apart as they approach the comet, flying past it from different angles to capture comprehensive data. High-resolution cameras will image the nucleus in unprecedented detail. Mass spectrometers will sample the coma directly, measuring the exact composition of venting gases. Dust analyzers will collect and analyze particles, revealing the mineralogy and organic chemistry. Magnetometers will measure any magnetic fields associated with the comet. In a single flyby lasting just minutes, these instruments will gather more detailed information than months of telescopic observations could provide. Dr. Geraint Jones, principal investigator for Comet Interceptor, explained the mission's philosophy. "We learned from Oumuamua that we can't afford to be caught unprepared. By the time you design, build, and launch a spacecraft in response to a discovery, the target is long gone. Comet Interceptor flips that model. We launch first, then wait for nature to deliver the target. When the next pristine or interstellar comet arrives, we'll be ready to meet it." But Comet Interceptor won't launch until 2029, and spacecraft take years to reach their operational positions. What about objects arriving now? Like 3i/Atlas for those. The strategy is different: maximize ground-based and space-based observations, and apply lessons learned to improve detection capabilities for future visitors. One of the most important developments in this area is the Vera C. Rubin Observatory, currently under construction in Chile and scheduled to begin operations in 2025. The Rubin Observatory will revolutionize how we find transient and moving objects in the solar system. Its 8.4-meter primary mirror and enormous 3.2 gigapixel camera will scan the entire visible sky every few nights, capturing images of billions of stars and galaxies. But more importantly for interstellar object detection, it will automatically compare each night's images to previous observations, flagging anything that moved or changed brightness. The software can identify asteroids, comets, variable stars, supernovae, anything that wasn't in the same position or didn't have the same brightness as before. This capability is transformative for finding interstellar objects because it dramatically increases the survey volume. Current surveys like Atlas, Pan-STARRS and Catalina Sky survey cover large areas of sky, but they revisit the same regions only every few days or weeks, and they can only detect objects brighter than certain magnitude limits. The Rubin Observatory will be faster, deeper, and more comprehensive. Simulations suggest it could detect one interstellar object every year, possibly more compared to the 3 we've confirmed in the past 7 years with current surveys. Think about what that means. If Rubin Observatory discovers 10 or 20 interstellar objects over the next decade, scientists will be able to study a population of these visitors, not just individual oddities. They can compare compositions, trajectories, sizes, and activity levels. Are nitrogen-rich comets like 3I/Atlas common, or are they rare? Do interstellar objects come from preferentially certain directions in the galaxy, suggesting they're being ejected from specific stellar nurseries or clusters? Are there inactive interstellar asteroids that pass through undetected because they don't develop visible comet? Dr. Mario Jurek from the University of Washington, who leads the Rubin Observatory's data processing efforts, outlined the potential every interstellar object we detect is a free sample return mission from another star system. We didn't have to travel light years to collect it. It came to us. With Rubin survey power, we're going from studying individual curiosities to building a statistical sample that can tell us about the demographics of planetary systems across the galaxy. How many ice giants do typical systems have? How efficient is the ejection process? What are the chemical fingerprints of planet formation in different stellar environments? Beyond dedicated surveys, there's growing interest in rapid response observation networks. When an interstellar object is detected, the discovery needs to be announced immediately so observatories worldwide can respond. The Minor Planets Center, which coordinates asteroid and comet observations, already has protocols for fast dissemination of data, but improvements are ongoing. Automated systems can now trigger observation programs at robotic telescopes within minutes of a discovery, starting data collection before human astronomers even review the initial reports. Amateur astronomers are joining this effort too, with commercially available telescopes, sensitive cameras, and spectroscopic equipment becoming more affordable. Skilled amateurs can contribute meaningful data. When 3I/Atlas was discovered, amateur astronomers around the world measured its brightness, tracked its position, and even attempted spectroscopy. Their observations supplemented professional data and provided continuous coverage during periods when large observatories couldn't access the target. It's a democratization of science. The study of interstellar visitors isn't limited to researchers with access to billion-dollar space telescopes. Anyone with the right equipment and knowledge can participate. But perhaps the most ambitious proposal for future interstellar object studies doesn't involve detecting them in our solar system at all. It involves chasing them down in interstellar space. Project Lyra, a mission concept studied by the Initiative for Interstellar Studies, proposes sending a fast spacecraft to catch up with Oumuamua or other interstellar objects after they've left our solar system. Using gravitational assists from Jupiter and the Sun, combined with advanced propulsion systems, such a spacecraft could theoretically accelerate to velocities high enough to overtake an interstellar object within a decade or two of launch. The engineering challenges are immense. Velocities would need to exceed 100,000 miles per hour. Navigation would require unprecedented precision, and the spacecraft would need to function autonomously across interstellar distances where communication delays stretch to hours. But the scientific payoff would be extraordinary close-up imaging, direct sampling, maybe even landing on the object's surface. You'd be studying an interstellar visitor in its natural environment, the cold, dark space between stars, rather than the disturbed state it's in when heated by our sun. Would you volunteer to work on a mission like that, knowing the spacecraft might not reach its target for 20 or 30 years, and you might not see the results in your career lifetime? That's the kind of long-term thinking required for interstellar object science. and it's a testament to how seriously researchers take these opportunities. 3I/Atlas has taught scientists critical lessons. Nitrogen-rich comets from other star systems can exhibit extreme outgassing at large distances from the Sun. Non-gravitational acceleration from venting can significantly alter trajectories, and rapid spectroscopic follow-up is essential to capture chemical data before the object fades. These lessons are shaping plans for future observations, influencing mission designs, and preparing humanity for an era where interstellar visitors are no longer rare surprises, but expected arrivals that were equipped to study in depth. And that brings us to perhaps the most profound realization emerging from the study of objects like 3I/Atlas. What it means for our understanding of our place in the galaxy, and the messages written in ice that are constantly arriving from distant stars. For most of human history, we could only wonder what existed beyond our solar system. The stars were distant points of light, beautiful but unreachable, their secrets locked away by the vast gulfs of interstellar space. We developed theories about how stars formed, how planetary systems coalesced from disks of gas and dust, how different chemical environments might produce different types of worlds. We built increasingly powerful telescopes to detect exoplanets, planets orbiting other stars, and by the early 21st century, we'd confirmed thousands of them. We could measure their sizes, estimate their masses, sometimes even analyze their atmospheres when they passed in front of their parent stars. But these were always remote observations, indirect measurements, inferences drawn from faint signals travelling across light years of space. Interstellar objects changed everything. When Oumuamua arrived in 2017, followed by Borisov in 2019 and now 3I/Atlas in 2024, humanity gained something unprecedented: physical samples from other planetary systems, delivered to our doorstep by the galaxy's natural dynamics. We didn't need to send probes across interstellar distances or wait centuries for spacecraft to reach nearby stars. The material came to us, carrying chemical fingerprints and structural clues about worlds we'll never visit but can now study directly. Consider what 3I/Atlas has already revealed. The nitrogen ice venting from its nucleus tells you that its parent system had cold outer regions where nitrogen could condense, regions analogous to our Kuiper belt, but existing around a different star. The carbon monoxide abundance suggests a chemical environment rich in carbon and oxygen, locked into simple molecules during planetary formation. The organic compounds detected in the coma indicate that complex chemistry occurs even in the frozen darkness of interstellar space, building molecular diversity over millions of years. The size of the nucleus, roughly 1.5 kilometers across, gives you a data point for the scale of objects ejected from planetary systems. The non-gravitational acceleration from outgassing teaches you about the dynamics of volatile sublimation far from stellar heat sources. Each of these details is a piece of a much larger puzzle understanding how common Earth-like conditions are in the galaxy. Do other planetary systems have icy outer regions filled with volatile-rich comets like ours? Are nitrogen-rich worlds comparable to Titan, Triton, or even Earth with its nitrogen atmosphere common or rare? When planets form around other stars, do they follow similar chemical pathways, producing similar ratios of water to carbon dioxide to nitrogen? Or does each system develop its own unique chemical signature? Dr. Karen Meach from the University of Hawaii, who has studied all three confirmed interstellar objects, reflected on the broader implications. Every interstellar visitor is teaching us that planetary systems are diverse. Oumuamua showed us objects with unusual shapes and trajectories. Borisov looked remarkably like our own comets, suggesting some universal formation processes. 3I/Atlas reveals nitrogen-rich compositions that tell us about cold outer system environments. As we discover more, we'll build a statistical picture of what's typical and what's exceptional. This is comparative planetology on a galactic scale. Think about the questions you can start answering with a larger sample of interstellar objects. If you detect 10 nitrogen-rich comets over the next decade, you'll know that nitrogen ice is common in the outer reaches of planetary systems. If you find that 30% of interstellar comets show high carbon monoxide abundance, you'll learn something about the typical carbon-to-oxygen ratios in star-forming regions. If half the objects are inactive asteroids, while the other half are active comets, you'll understand the relative populations of rocky versus icy bodies ejected from planetary systems. This isn't just academic curiosity. The composition and abundance of volatiles in planetary systems directly affects the potential for life. Water is essential for life as we know it, but so are other materials: carbon for organic molecules, nitrogen for amino acids and nucleic acids, phosphorus for energy transfer, sulfur for protein structure. If we discover that nitrogen-rich comets like 3Y/Atlas are common, it suggests that many planetary systems have abundant nitrogen available for incorporation into planetary atmospheres and biospheres. If water-rich comets like Borisov are more typical, it tells us something different about the delivery mechanisms for life's ingredients. There's also a humbling perspective shift that comes from studying interstellar objects. For centuries, humans viewed our solar system as the template, the standard, against which all other systems would be measured. We expected to find solar systems with rocky inner planets, gas giants in the middle, and icy bodies in the outer reaches, all orbiting a sun-like star. But exoplanet discoveries revealed shocking diversity: hot Jupiters orbiting closer to their stars than Mercury orbits our Sun, super-Earths with no equivalent in our system, planets in eccentric orbits, worlds orbiting binary stars. Our solar system isn't the template. It's one example among billions, each shaped by slightly different initial conditions, different formation histories, different evolutionary pathways. Interstellar objects drive that lesson home in a visceral way. You're not looking at telescope data of a distant exoplanet. You're analysing actual ice, actual organic molecules, actual minerals from another star's planetary system. This nitrogen didn't come from our solar nebula. It condensed in a completely different stellar environment, possibly billions of years ago, and drifted through the galaxy until gravity happened to steer it into our neighbourhood. The carbon monoxide molecules in 3I/Atalas's coma formed around another star, in conditions we can only infer, shaped by processes that might have been similar to ours or radically different. What does it feel like to realise you're living in the first generation of humans who can study material from other star systems? Not just detect it remotely, but actually analyse its composition, measure its properties, track its behaviour. You're witnessing the birth of a new scientific field, interstellar material science, and the discoveries are just beginning. By 2030, if predictions about detection rates hold true, we could be tracking interstellar objects regularly, perhaps several per year. Each one will teach us something new. Maybe we'll find a comet rich in water ice, suggesting a formation environment closer to its parent star. Maybe we'll detect an asteroid made of pure iron, possibly a fragment from a planetary core destroyed in a catastrophic collision. Maybe we'll discover an object with organic molecules so complex they hint at prebiotic chemistry. Each visitor carries a story written in its composition, and humanity is learning to read those stories. The technology is advancing rapidly. Future space telescopes will have even greater sensitivity than James Webb, capable of detecting fainter objects and analysing finer spectroscopic details. Missions like Comet Interceptor will fly through cometary comae, sampling them directly rather than observing from millions of miles away. Improved survey telescopes will catch interstellar objects earlier in their approach, giving scientists months or even years of observation time instead of weeks. Artificial intelligence and machine learning algorithms will sift through vast data sets, identifying patterns and correlations that human researchers might miss. But perhaps the most exciting prospect isn't technological, it's conceptual. As we study more interstellar objects, we'll develop a new understanding of the galaxy itself, not as a collection of isolated stellar systems, but as an interconnected ecosystem where material constantly flows between stars. Comets and asteroids are ejected from forming planetary systems, wander through interstellar space for millions of years, and occasionally get captured or pass through other systems. Material from one star's planets can seed another star's worlds. Organic molecules synthesized in one planetary system can be delivered to another. The galaxy is mixing itself, redistributing the building blocks of worlds across hundreds of light years. This has profound implications for the origin of life. If comets can transport organic materials between star systems, then life's ingredients, or even life itself, in the form of dormant microorganisms frozen in ice, could potentially spread through the galaxy via natural processes. It's called panspermia. The idea that life might not originate independently on every world but could be transported between them. Most scientists remain skeptical that active organisms could survive the radiation exposure and extreme cold of interstellar space for millions of years. But organic molecules certainly can, and those molecules could seed the chemistry that eventually leads to life. Dr. Chanda Prescott Weinstein from the University of New Hampshire, who studies cosmology and the physics of ice, offered this perspective. Interstellar objects remind us that we're not separate from the rest of the galaxy. We're part of a larger system, connected by gravity, by chemistry, by the flow of matter across space. The ice that's venting from 3I/Atlas right now contains atoms that might have been forged in a supernova billions of years ago, incorporated into a planetary disk around a young star, frozen into a comet, ejected into interstellar space, and now delivered to our solar system. Those atoms are part of a cosmic cycle that has been running for the entire history of the galaxy. You're living in a remarkable moment, the decade when humanity learned to read messages written in ice from other star systems, when we transition from wondering what exists beyond our solar system to actually studying it directly. 3I/Atlas, with its impossible 10,000 kilometer plume powered by nitrogen ice from an alien world, is just the beginning. More visitors are coming, carrying more stories, revealing more secrets about the galaxy we inhabit. And you're here to witness it, to learn from it, and to marvel at the fact that the universe delivers its wonders right to our doorstep if we're patient enough to watch and curious enough to ask.